This is Professor Nathan Smith. I'm recording this lecture for my degree completion students in Visalia and North Fresno. This is Chapter 5 on demand estimation. So, as you can imagine, demand is very important to many firms. Business plans can succeed or fail depending on whether there's demand for products that they're making. So businesses want to know something about this. But the situation is not as simple as in some of the charts that we've shown in this class so far. It's not, firms can't just observe what the demand curve is. Well, they observe something a little bit different. They may charge a particular price, and they can see how much people will buy. They'll find out ex post. So one issue is you want to be able to predict ex ante how much people will buy at a given price. But even ex post, you only know how much they demanded at one particular price. You don't know what the whole demand curves look like. Remember, this demand curve is a whole set of hypothetical statements. So if the price were here, quantity would be such and such. If the price were here, quantity would be such and such. This chart shows what we can call the identification problem. So it's if you have a set of points, and if both the demand and supply curves are moving, which is very typical, then you would like to know, if you want to know what the demand curve is like, then, well, you could sort of try to guess by just seeing what's happened to price, and then deduce, see what's happened to price, see what's happened to quantity, and then try to deduce a demand curve from that. But that might be quite an invalid procedure if, in fact, the demand curve itself is moving. So let's take this example. We've got sort of 4 maybe time periods, or whatever they are. 1, 2, 3, and 4. So maybe, as time goes, a company's costs are rising, it's reducing supply of some good, and the company would like to know what the demand curve is. And so, well, according to, if they just naively looked at their data, they said, okay, so we used to charge P1, and we sold Q4, then we charged P2, and we sold Q3, then we charged P3, and we sold Q2, then we charged P4, and we sold Q1. So we just string those points together, and then extrapolate what goes on beyond the boundaries and in between the points, and we've got our demand curve, right? Well, no, because in this case, so these D1, D2, D3, and D4, these supposedly represent the real demand curve, somehow known, but maybe nobody in the economy knows it, but since we're just using it as an example, we can make up the truth of the case however we want. So we'll assume that D1, D2, D3, and D4 are the real demand curves at these times. Well, okay, so what's going on here? Real demand is increasing. There's actually an increase in demand for this product, even at the same time as there's a reduction in supply. And what this causes is it makes the demand curve look steeper than it really is. Because these increases in demand are offsetting the effects of higher prices, they're making the demand curve look a lot steeper. So if maybe the firm is operating up here, and they're under the belief that if they drop the price to P1, they could only sell Q4. But actually they could sell a lot more, because you notice this demand curve is much higher and rather flatter than the one they estimate. So this is an example of the identification problem. And in general, if price and quantity are determined jointly by demand and supply, then you can't figure out demand or supply just from movements in the other curve. You can only do that if you assume that demand isn't changing. Then you could come up with a decent estimate. But if demand is likely to be changing as much as supply is, then you won't be able to estimate this way. Okay, so how do we estimate the shape of the demand curve if we are moving past this naive way of doing it? So, first of all, there are a number of methods which are not exactly maybe as scientific as we'd like, but may be of some use. So one would be consumer surveys. So you could ask consumers, how much beer do you buy each month, or how many gallons of gas do you buy each month, how many tacos do you buy each month, how many do you plan to buy in the future, and that's actually not enough, because you want to know not just how much they buy, but how they're responding, how they would respond to price. So here you're asking if the price of beer rose by $1 a glass, how much of it would you buy? If tacos were $4, then how much would you buy? And so on. As you can imagine, consumers might find it difficult to answer these surveys in a really accurate way. Consumers probably don't know even what their behavior really is in terms of how many tacos they buy in a month. Still less do they know what they'll decide to do in future, because their habits might change in ways that they'll find it hard to predict. But also, they're particularly unlikely to be able to estimate accurately how they will respond to a change in prices. So this might be of some use, but it needs to be taken kind of with a grain of salt, these consumer surveys. Observational research. Yeah, you can see what consumers do in the market in practice. Consumer clinics, you can set up a laboratory which kind of mimics a market and then see how consumers respond. So you do market experiments. Now this is one where you're using you're actually changing your prices in particular markets. So maybe you're a company that's selling goods in a lot of different places. You could raise prices in some, lower prices in others, and then see how demand is affected by that. So this, I believe, is based on a market experiment. So they changed prices of particular kinds of oranges and then found out how much people responded to changes in these different prices. So price elasticity and cross-price elasticity. I hope you remember what an elasticity is. It's the percent change in one thing over the percent change in something else. So first of all, so the price elasticity of demand for Florida Indian River oranges, there's a change in demand for this kind of orange, then there would be 3 times as large a percentage change typically in, if there's a change in price, there would be 3 times as large a percentage change in demand, quantity demanded, and that's sort of similar for the other two, I guess. But then we can also look at the cross-price elasticity. So if there's a change in the price of Florida Indian River oranges, how much does that affect? What's the percentage change in the quantity demanded of Florida interior oranges? That's plus 1.16. So as you'd expect, these numbers are negative. All of these numbers are positive. So when these prices fall, these are substitutes for each other. They're different kinds of oranges. So when the price of one kind of oranges falls, then quantity demanded for other oranges rises. So that's an empirical result. This, I think, is not an empirical result. It's just an example, but this shows the link between advertising expenditures. Well, it shows sort of a data series of advertising expenditures and sales revenues, and yeah, obviously it's not real data because the years are numbered from 1 to 10, or at least that suggests it's probably not real data. But so here you might be interested in, if we increase advertising revenues, how does that affect sales? But again, that's kind of assuming that demand is always the same function of advertising revenues and of other advertising expenditures and other factors in the market. Okay, let's try to analyze the effect of advertising expenditure on sales a little bit more deliberately. So in this case, we've just drawn all these points in a scatter plot. In fact, they link this all together. You notice we're drawing lots of different lines, the intuition that that you're supposed to be able to get here is that there will be some line that can be drawn among these points. It's probably something like this, something like what I'm drawing here with the cursor. That will be the line of best fit. You can kind of see that by eyeball. If I just told you draw a line that runs between these points, then I'm sure you would probably be able to do it, and you draw a line that looks much like the one here. But that's somewhat unscientific, and if multiple people did it, they'd probably draw lines that look similar, but not exactly the same. So we want to come up with kind of a more scientific, a more systematic way to do something similar to what we would just do by eyeballing it. So we're assuming there's a relationship between these two variables. Now, the fact, by the way, that this is basically a time trend, so advertising expenditures seem to be rising and sales seem to be rising. Well, that might make you a little suspicious. Maybe something else is going on rather than just the advertising increasing sales. It might be just economic growth and affecting demand. And so you'd have to be careful about drawing these kinds of conclusions. But at any rate, but still, it serves as a good example. So, okay, once again, we have the sales revenue against advertising expenditure represented graphically. Now, regression analysis, this is really crucial this is probably the most important application of statistics in economics. Economists like running a lot of regressions, and what you do when you run the regression is you basically look for what's called the line of best fit. So this is kind of the same as if you eyeballed it, you'd say, well, what line sort of fits the best through these points, and you'd probably draw something that runs kind of through the middle. But we're now going to think about that process more mathematically and formally, and we'll define the regression line as the line that minimizes the sum of the squared vertical deviations of each point from the regression line. That's probably not very obvious. There's sort of a lot packed in there. Some you understand. The squared vertical deviations, that's probably the hardest part to understand. This, by the way, the label for this is ordinary least squares method. Okay, this shows you the vertical deviations. Some of these points are a little bit misleading. Like, I don't know why they drew a line between E7 and E8. But let's focus on E9 and E10, for example, or E2, or E1. These are all clear cases. It's sort of true in E6, E4 as well. In each case, we've drawn a regression line. We've drawn some kind of line between the points. I think this is the regression line. But each point, the points don't fall exactly on the line. And you wouldn't be able to draw a line in which all of the points fit perfectly, because that's just not how the points are distributed. They're not arranged in a line. If they were arranged in a line, then a regression would reproduce that line, but they're not. They're a little bit off, but once we've drawn the line, then we can calculate the distance from the line to each of the points. So that is called the vertical deviation. Then if you simply square that and then add them all together, so you take this, square it, add that in, take this, square it, add that in, take this, square it, E6, vertical deviation of E6, add, square it, and so on. You add all those up, and then you get the sum of squared deviations. And the point is to pick the line that minimizes that quantity. So what we call the model, this is where we say, well, we assume that y is a linear function of x, but with some kind of an error term. So there's some variation, but it's basically a linear function of x. And then we assume that that function takes the form of having a coefficient or an intercept and then a slope. So it has an intercept and then a slope coefficient here. So this a and b. So we assume that the model has this form, and then there are some errors. So what the regression gives us is it estimates the values of a and b. And then the error that's left over is just whatever the difference is between yt and y hat. So for some particular prediction, there will be some set of errors, and then we can, if we square those errors and then add up the sum, that's the quantity that we want to minimize. This is expressing it more formally, so you want to minimize the sum of squared errors. The errors are equal to yt minus the predicted y hat t, the predicted value of y for those values of the independent variables. And so then you can define the errors then again as you just basically substitute in the formula for y hat. This gives you the sum of squared errors. And it turns out that the b hat and the a hat that minimize the sum of squared errors are determined by this formula. Now let me tell you a little more about this formula. You don't really need the formula. You don't need to know it. You don't really need to be able to reproduce this formula. The truth is, I don't really have this formula memorized. It actually would come in different forms depending on for a simple. Maybe I could remember this one. This one's fairly simple because it's just for one regression, but you can look it up when you need it. But furthermore, you usually don't need to apply it yourself. A lot of times you can use software programs that use it. So during my master's degree, then I learned this stuff, but then I didn't remember the details of how regressions were actually run, but I knew how to punch them into software packages, and then I got some jobs for a few years where I was running a lot of regressions, and I was just using the software packages. And then I went back to grad school, and I reviewed it, and now I definitely understand it, but I still, again, may not always remember the formula. It's important to understand the formula, and at least to know what some of these terms mean. So again, first of all, what's this x? What are these x's? What are these x bars? What are the yt and so on? What does everything in this formula mean? Well, okay, first of all, the summation sign. There are a certain number of observations, n observations in particular. So the idea of this summation says, okay, sort of work your way through all of the observations. Go through all the observations for each one, then you want to add something into this sum, and then this expression says we're interested in the sum of all those. Okay, what expression are we adding into that summation? Okay, well, first of all, for each t, for each of these numbers from 1 to n, there's an observation. That means there's an xt and there's a yt. That's what an observation consists of. So those exist. But we're interested in the deviations of these values from some mean. So we'll choose x bar, the average of x. Calculate the difference there. So is x above average or below average, and by how much? Similarly with y, we'll calculate y bar, the average value of y, and then for each observation we calculate is this observation above y bar or below by y bar, and by how much? And then down here we have again, is the observation above x bar or below x bar, and by how much? But then we square that value. Then we divide, and then that gives us our beta. And once we have the beta, then we can plug that into this formula. So that's the procedure for ordinary least squares with a single regression variable. And the formula for multiple regressions is actually fairly similar to that. So this just gives you an example of this formula being applied. So we're interested in, okay, we have n equals 10. We're interested in the sum of the xt's. Well, the sum of the xt's we need because it comes down here. The sum of the yt's we need, it comes down here. Remember, x bar and y bar are part of our formula. The sum of the xt's is actually not. Nowhere in here does the sum of xt appear, or yt for that matter. But x bar appears and y bar appears, so that we just sum up all the x's and then divide them by n, the number of x's, and that gives you x bar. This gives you y bar calculated by the same means. We're interested in, for the denominator, we need to know this formula. So we take this x bar, we plug it in here, and then we loop through all of the observations, and for each one we calculate xt, the x value for that variable, minus x bar, and then we square each value, then we sum them together, then that gives us, in this case, 30. It's funny that it worked out that neatly, but and similarly, then we plug these into the numerator. So we take each xt, subtract x bar, each yt, subtract y bar, multiply those together, add them all up, we get 106. So then we get our value for b hat, estimated 3.533. We get our value for a hat, estimated 7.6. And so that's our regression. Okay, so we can continue. This is just all the same information, it's just blown up so it's easier to read. Okay, now, whenever you run a regression, you'll find some slope estimate. And the interpretation of the slope estimate is that this is how much the dependent variable, so your y, for example, whatever variable you think is dependent, this is how much it changes in response to some change in the independent variable. But there's always, pretty much always, just by random chance, there will be at least some slope. And if you see some slope, that tells you that it tells you in principle that the variables are related, but it could just arise randomly. And so the key is to figure out, does it arise randomly? Could it have arisen randomly? Or can we be confident that there's some real relationship that is being revealed here? And this is where we bring in significance testing. So the standard error of the slope estimate, this is where things get even more complicated, but we're interested in degrees of freedom down here. This is called degrees of freedom n minus k, so k is the number of variables that are included in your regression. So far we've only included one, so k would be 1, but they're showing you a more general case here. And then again, these are the vertical deviation. But notice now, we don't have y bar in here, we have y hat. So this is vertical deviation from the predicted values. But down here we do have the total deviations, the total volume of the deviations. This tells you the standard error of the slope estimate. And this shows you an example of it being calculated. Do you need to know that? Probably not. We think it's sort of good for you to have seen it. In any case, we didn't show you all the algebra by which it's derived, but you can come up with that estimate. This t statistic is a little more important. Not that you really need to know how it's calculated, but and then this is where it comes from. You take the beta hat, the slope coefficient, divided by the standard error of the beta coefficient, and these are kind of like in the same units. So this t comes out. It's a pure number. But the key is this t takes on some particular value, and that value allows you to tell whether the regression is significant or not. In this case, the degrees of freedom is 8. So for any particular degrees of freedom, then there will be some critical value of the t statistic that tells you at what's called a 95% confidence interval that the result was not generated randomly. So if the number is more than 2.306 or less than negative 2.306, that tells you that you can be confident that you're observing a real relationship there. It's not just coincidence. I mean, if you look at this chart, I mean, you can probably tell clearly there's a real relationship between if these x and y were just random, they were totally unrelated to each other. There's no way they would track each other that closely. There's no way you'd see an appearance of a correlation being that strong. So you could probably just intuitively you could say there's no way that's random. But what this whole procedure does is it sort of confirms that scientifically and in a way that could really establish consensus. I mean, you can imagine if you think for a moment about if you use regression analysis in a business meeting. Well, will most of your colleagues understand it? No, certainly not the details of it. They probably won't, unless you're working for a firm that is kind of really data driven and specializes in that kind of thing. But think about how impressive it is to say we ran a regression and it was statistically significant at the 90% level versus just saying, well, I eyeballed it and this kind of looked like it was the case. It'd be much more impressive if you're trying to sell something to a boss. It's useful for establishing consensus in a team. Maybe a couple people both look at a set of points, and some say, yeah, that seems like there's a real relationship there, and others say, well, I don't know, it might just be random. Well, this can establish consensus. And now the 95% confidence interval, that's just kind of a convention. It is what's typically used. People usually report 95% confidence interval. I mean, in this case, this t statistic is way above the critical value, so this would be significant at the 1% level, or the probably 0.1% level. I don't know how. There's definitely a relationship here. Okay, so we talked about the sum of squared errors. So how far does the independent variable deviate from the mean? Now, our regression tells us partly how far it varies. So the y-hats, they tell us partly how far some of the variation will be picked up by the y-hats, probably not all of it. So it turns out algebraically this has to hold. So if you subtract the y-hats, you see how far y-hat deviates from y-bar, then how far yt deviates from y-hat. You add those two together, you'll always end up with this. This is kind of like Pythagorean theorem stuff, but never mind. The key is that the total variation equals the explained variation, this stuff, plus the unexplained variation. So again, if you went back to, you say, well, why did we have so many sales in period 8? You say, well, first of all, one reason is that we were advertising more in period 8 relative to some of the periods where our sales were lower. You say, well, yeah, but E8, it's especially high. It's even above the regression line. We were advertising some, but we weren't advertising, more than or even as much as in period 9. And you say, well, okay, it's not a perfect explanation. We don't know exactly why it was so high in period 8. There may have been other factors, but a big factor was probably that we were advertising a lot in that period. So I was just giving a story that kind of distinguishes explained variation. In this case, it would be variation in sales that's explained by advertising, and unexplained variation. Variation that doesn't fit the story. You just are not able to interpret the influence of advertising on sales in such a way that that it explains all the variation, so there's some left over. So this gives an example. You've got the mean, y bar here. You've got, and I guess we are looking at E8, picking that period. say, how far was it above the mean? Okay, and you say, well, how much of that is explained by, how much of that is explained by our prediction, explained by advertising according to our prediction? Well, it's this part, yt bar minus delta y. How much is explained then by just is unexplained? How much do we not understand why? Well, this it measures how far that is. So this is breaking down variation into explained and unexplained. Okay, so the R squared can be called the coefficient of determination. It's calculated as explained variation over total variation, and R squared, in this case, it's 85%. So in this case, most of the variation is actually explained by differences in advertising. Now, in general, R squared is a measure of basically how powerful your explanatory result is. We talked about significance testing. That measures just whether you've actually found a valid result or not. So if it passes the significance test, that means there's a real result there. R squared refers to how much of the variation you're explaining. And it's possible to have, usually R squared will be high when you're succeeding in explaining, there will be a certain amount of correlation between a regression being significant and a regression having an R squared. But it's no necessary link. These are separate things. You could have a case where you run a regression, it's statistically significant, maybe highly significant, but the R squared is low. You say, well, it's clear that this is explaining part of the variation, but it's only a small amount. If it's a sales and advertising, you might get a case you had lots and lots of periods to observe, or lots and lots of different similar markets that you can compare. You might get a case where you say, well, it's highly significant that advertising does increase our sales, but it only explains a small amount of the variation. Mostly the sales get affected by other factors that we don't know what they are. Okay. So this is a calculation of R squared, and we're sort of working through, again, this is a summation, so you can think of it as you've got 10 different observations. In this case, since we're doing this laboriously, we're going through all the details. These are lined up in separate columns in a table. Gives you the YTs for each of those. And then, at the bottom, so we've got n equals 10 in this one. Here we say the sum of the YTs is 500, so Y bar equals 50. Then we subtract that in each of these cases, and we get YT minus Y bar. So this is an estimate of the total deviation. And then we square all of these, so YT minus Y bar squared. And that gives us the total sum of squares, sum of squared deviations. Okay, so now we've run our regression, we get YT hat, and YT hat predicts sales based on advertising. This isn't the real sales, this is the predicted sales. This is the real sales, this is the predicted sales. So this is trying to match this, and you notice that it sort of does. It's at least it's close. 46, 49, 48, 46, 52, 49, 54, 53, 58, 53. No, it's sort of close. So then we calculate Y hat minus Y bar. So this is the explained variation. Say, well, to what extent does can we explain the fact that Y is higher than its average value by the fact that advertising is higher than its highest value? Well, this is the explained variation, this is the square of explained variation, and then we can sum all of those and we get this. Sum all of those and we get this, and then if we take let's see here. Oh yeah. So this is the total variation. This is the unexplained variation. Column 8. So, and then r squared. Where's our formula for r squared again? Yeah, r squared is this divided by that, and you can see those numbers pop up here again. 373, 440. Jag. Irritating. This number's wrong. This is... Oh, no. No, sorry, this is the unexplained variation. So these two would sum up to that. They should, do they? They don't quite, do they? But they certainly come very close. So this is probably just, they're just rounding things off. But anyway, that shows you how r squared is calculated. Will you have to do that in this class? Probably not. Certainly not on a test. But you do want to know what this r squared means. You want to know, when you see an r squared, you want to be able to interpret it. That's the key. Coefficient of correlation. So this shows the strength of the correlation. It's we've got sort of lots of numbers that are related to each other. I mean, what's the meaning of this? The higher this number is, the more closely two variables are correlated with each other. Okay. So far we've talked about single regression analysis. Actually, I should probably close this and continue this in another video because it's sort of a new theme.